So, Happy New Year to all of you. Welcome in very first lecture of Math F242 Operation Research. So, hopefully, you all are safe at your place. So, I have shared the handout with you over the email and as well as on the AU GSD site. So, let us discuss the few things about the course. So, first of all, the textbook of this book is Taha Operation Research and Introduction, Pearson Education, 9th edition of 2014. So, from here, we will cover the three chapters, or you can say the four chapters. And second and important textbook is S. Venkateswaran and B. Birwal Singh, Operation Research EDD Notes. Only the part three. We have the three parts for this book, but in your course, we have only the part three. I will cover the part one, means first chapter from the part one, but there is no need to purchase. If you have, then it's okay. Otherwise, there is no need to purchase. Only you have to purchase the part three. Right? And following are the some reference book. So mainly, this course is categorized in the 8 modules, and each modules are absolutely independent. Right. Only you can say the first module is useful for all other modules. Otherwise, rest 7 modules are independent to each other. So, in the first module, we will cover about the introduction of the probability theory. So, whatever you have covered, all we will revise. Right. Whatever you have covered in the course Math F113 Probability and Statistics. So all we will revise here in the first 4 lecture. Here I will give you the idea about the probability distribution, expectation, and other basic theorems and concepts related to the probability theory. Thereafter, this is the in mathematics department. This is the most important course in view of the application. Here, whatever the topic you will see, all are the application oriented. So it's other means it is a totally application oriented topics we will cover here. So in this case, in the second module we have the worth and means we have the queuing theory or waiting line problem or the congestion. We, here we will discuss the mathematical modeling of congestion, situation of the congestion, the situation of the waiting. Means we have to wait at every point, whether in the grocery shop, whether over the telecommunication, whether over the computer network, everywhere we have to wait. So how we can do the mathematical modeling, right? That we will cover in this. Now, in the module 3, we will cover the inventory model. Inventory model means we have to maintain the inventory to satisfy the demand, inventory of the goods, inventory of the items. So how we can, because the demand is unpredictable in nature, so we cannot judge how much inventory we have to maintain, right? So that type of the things you can cover in the inventory. Then another important topic is reliability theory. So that whatever the machines you are using, whatever the components you are using, whether the TV, fridge, computer, you want it should be the reliable. But failure is unpredictable in nature. So in this chapter, we will cover the theory of reliability. Thereafter, we have the game theory. So in the game theory, both the opponents want to win. So how we can do the mathematical modeling of the game? Thereafter, we have dynamic programming. So dynamic programming, in this, it is the extension of the linear program little bit, and you can solve other kind of the problem also. But in this, what we have to do, we have to divide the problem into the sub problems, and step by step we solve the sub problem, so that at last we have the solution of the complete problem. Then after, last topic is the CPM part. So in the CPM part, we we will understand how to schedule the work, how to plan the work, right? So that we can complete our assignment on time. So these are the following topics that we will cover in the coming lectures. And here we have the tentative evaluation component, right? So mid semester of 90 minutes as per guidelines of the AUGD, but it may change as per the condition. So mid semester 90 minutes of 30% weightage, comprehensive examination of 180 minutes of 40% weightage, and tutorial quiz assignment, right? It is of 30% weightage. And you can find all the means link for the lecture for Monday and Tuesday, Thursday series here, and you will find all the recorded video on this YouTube link, and day-to-day basic information on this WhatsApp group. So I advise all of you to join the WhatsApp group so that you can get the information as quick as possible. So from your side, any doubt about the course? And another important thing, operation research is the extension of optimization. Means here also we optimize. There you have optimized, there you have seen, there also you have covered the many application, right? So it is the extension of that. Only the difference is, can you judge, anyone can tell what is the difference between the optimization and the operation research? Because you will find the text in the name of the operation research everywhere. Means optimization and this operation research are the synonyms to each other. So why we have the two course here? Anyone, can you judge? In the optimization, whatever the topic you have covered, all are deterministic in nature. But whatever the topic here you will cover, right, all are probabilistic in nature. Right? That's why the probability is important here. Clear? So that is otherwise more or less both are the same course. So in many university you will find the mixture of these two courses, but here we have the classified as a two course. One depend over the all are the deterministic in nature, and here all are probabilistic in nature. So anything you want to ask about the course, any students? This is the easy course, scoring course, but here uh, I have seen the students do the lot of calculation mistakes, and due to that they lose the marks, right? So be careful, because here we have the lot of numerical. Anyone, any doubt about the course? So I believe that there is no doubt. Great. So now let us start with the first thing. So in the first four lectures, we will revise 4 or 5 lectures. We will revise the basic probability theory. So I believe all of you know all the things, but lot of things means I will brush up here so that you can use in the coming chapters. So let us start. So here we will study the basic of the probability theory. So probability theory or the theory of the stochastic process. Stochastic means a dynamic, right? A probabilistic. So here means here we will study the whatever the process are probabilistic in nature. We will study the theory about that. So you know that probability deals with the random outcomes of an random experiments. As you toss a coin, so whether the head will come or tail will come, so it is probabilistic in nature. So probability theory deals with such random outcomes of an random experiment. So in this, we have the one technical term. What is an experiment? Because in the laboratory, in the lab, you have done so many experiment. So you have the idea what is the experiment. The activity whose outcome whose outcome is to be observed, right? So it may be the Ohm's law experiment, means you supply the voltage, you have the known resistance, so you can judge what will be the current. So because here we have the fixed formula V is equal to IR, so such kind of the experiment are deterministic in nature. So here we have the deterministic experiment where the sure outcome to be observed, means we know in advance certainly what the output will come, right? So now we have the another kind of the experiment, random experiment or the probabilistic experiment, where we cannot predict what will be the possible outcomes. We know only the possible outcomes, we know only the possible outcomes, but what will be the outcome that we cannot judge. So that is the random experiment or the probabilistic experiment. So when the experiment is conducted, the outcome cannot be predicted in advance. We know only the possible outcomes. Means when we toss a coin, we know the possible outcome can be the head or tail. But what will come, that we cannot judge. We cannot predict. So that type of the experiments are known as the random experiment. So it may result one outcome out of the several possible outcomes. The outcome is subject to chance, right? That is important. So here the outcome is subject to chance. So depending over this, we have to develop the theory. So it is capable of being repeated indefinitely. So here, whatever the stochastic process we will study, that must have the quality that you can repeat that indefinitely. Means you can toss a coin number of times under the essentially the same condition. Means for the stochastic process, the basic condition must be same. It is characterized with the statistical regularity. I will tell you later on what is the meaning of the statistical regularity. Statistical regularity means after the so many repetition, the chance, the probability of getting one outcome, one possible outcome will be the same, right? Will be the constant. For example, when we are tossing a coin, one time it may have the head, so we cannot say that probability is equal to 1 or probability of head is equal to 1 or probability of tail is equal to 0. We have to repeat the experiment number of times. For example, 10,000 times, 1 lakh times. So what will happen? Out of the 10,000 times, might be means 5,010 are ahead and 4,990 are the tail, right? So means as you increase the number of trial, number of repetition. So the ratio of number of the favorable event divided by the total number of the repetition tends to the constant value. That is the statistical regularity. Means when we have higher times repetition, n tends to infinity, the ratio of na upon n, right, number of the favorable outcomes. So na upon n should tends to constant. Then we say it follow the statistical regularity. Thereafter, we have the important terms: sample space, set of all possible outcome of the random experiment. For example, when we toss a coin, possible outcome is head and tail. So for that, the sample space we denote by the omega, and we enclose the all the possible outcome. Then after, we have the elementary events, the singleton set, each consisting of the single outcome. That is known as the elementary event. Just we enclose one outcome in the braces, so that represent the elementary event. So let us have the example. If you have the three coins, fair coins, and you toss them, so here the sample space will be the head, 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 tail, or tail, tail, tail. The same, if the if we toss the three coins and we are interested for the number of heads. So the number of heads can be the 0, 1, 2, 3. Means you can observe, here also we are tossing the three coins, here also we are tossing the three coins. Depending over the outcomes, we have the different sample space. In the first, we want the face value. In the second, we just want to count the number of heads. Then after, how many tosses required to get the first head? If you're tossing a coin, a fair coin, right, a single coin. So now we want when the head will come. So might be in the very first toss you can get the head, or first tail then second head, or first two tails then third head, and so on. So in that case, we have the sample space as a 1, 2, 3 dash dash dash. So you can observe, just by tossing a coin, right, we have the different sample space. So sample space always depend what we want, over which we are interested. Then after, a point is chosen at random on the interval 0, 1. So let us have this a line. Here we have the 0, here we have the 1. So here we have the infinitely many points. So in this case, the sample space will be the any x between 0 and 1. So that is the way to represent the sample space. So from here, we can categorize the sample space into as discrete sample space and the continuous sample space. What is the meaning of the discrete sample space? When number of points in sample space is finite or countable infinite, then we say they are the discrete. For example, here we have the 8 elementary events. Here we have the 8 elementary events. Here we have the 4 elementary events, right? Means number of sample point in sample space are finite. Then we say it is the discrete in nature. In this case, the sample points or elementary events are infinite, but they are the countable infinite. Then the first three are discrete sample space. First three are the discrete sample space, but in the fourth, here we have the sample point as a uncountable, right? Uncountable. So in this case, it is the continuous. So here we can see that the first, second, third sample space are discrete in nature, but in the fourth one we have the uncountable sample points, right? So it is the continuous sample space. So that is the basic of the sample space. Then we come to the event. So the subset of the sample space, any subset E of sample space omega is known as the event. So an event E is said to have occurred if the outcome of random experiment is member of the subset E. For example, when we are rolling a die. So when we are rolling a die, at that time, what is the sample space? Sample space is 1, 2, 3, 4, 5, and 6. Now we want the event as a even number. Even number. So at that time, it is the 2, 4, and 6. So when we say event E is said to have occurred, if the outcome of the random experiment is member of the subset of the E. If you have either the 2 or 4 or 6, then we say event E or event of the even number has occurred. Now, laws of the event. So you have the idea what is the complementary event. So complementary event means E does not occur. If I am saying that E is the even number, E is even number, so its complementary event is the odd number. So when odd is occurring, so E is not occurring. So E does not occur, that represent the complementary. Then the intersection of the events. Intersection of the events means if each event even E to En occurs. If we have the multiple events and each event is occurring, it means we are computing the intersection of the events. Intersection of the events. For example, here we have the rolling random experiment is rolling a die. Rolling a unbiased die. So we know that sample space is 1, 2, 3, 4, 5, and 6. Let us define event E1 as even number. Even number. So the sample space will be the 2, 4, 6. Let us define the second event as number greater than 3. Number greater than equal to 3. So the sample space will be the 3, 4, 5, and 6. So if you compute the E1 intersection E2, the common point will be the 4 and 6. So here you can see both E1 and E2 are occurring. So that represents the intersection of events. Then union of events. So union of events we write as a union from 1 to infinity if we have the infinite events. If at least one of the event E1, E2, En occurs, then we say union of E1, E2, En occur. Thereafter we have the two events, sure events and impossible event. Means sure event means always occur. Always occur means the sample space. When you roll a die, out of 1, 2, 3, 4, 5, 6, always we have the one result. So that is the sure event, always occur. Impossible event, the event never occur. We represent it by the 5. Right? It is the empty subset of the sample space omega. Then after we have the event E implies event F. Means when event E is occurring, so always it implies that event F is occurring. So whenever E occurs, F occur. Right? So means E implies F. Here we have the E implies F. That is the if and only if E is subset of the proper subset of the F. Means when E is occurring, automatically it implies that F is occurring. Then after we have the E minus F, that represent when E occur but F does not occur. E occur but F does not occur. So here E is occurring. Here we have the E. Here we have the F. So at this E is occurring but F is not occurring. F is not occurring. So that we represent as a this area is the what? E minus F. E minus F, or it is equal to the E intersection F complement. Now you have the basic idea about the laws of the event. The events follow the commutative law, associative law, distributive law, and De Morgan law. After that, we have the important term mutually exclusive event. So mutually exclusive event, if E intersection F is phi, impossible event, both cannot occur simultaneously. Right? So here, for example, if you define the E1, E2 as a even number in rolling a die, if the experiment is rolling a die, right, and E2 if you define as a odd number, so we know that even intersection E2 is equal to phi. Even intersection E2 is equal to phi. So when even number is occurring, odd number cannot occur. If odd number is occurring, even number is cannot occur. So their intersection is phi. When we are talking about the mutually exclusive, let us have the three very important point about the mutually exclusive. If we have the three events, if we are saying that E1, E2, E3 are mutually exclusive, that automatically implies that they are the pairwise mutually exclusive. Pairwise mutually exclusive means E1, E2, E2, E3, and E1, E3. Right? Never we say that E1 intersection E2 intersection E3 is equal to phi. Then we say E1, E2, E3 are mutually exclusive. Right? When we say E1, E2, E3 are mutually exclusive, it implies that they are pairwise mutually exclusive. Means E1, E2 are mutually exclusive, E2, E3 are mutually exclusive, and E1, E3 are mutually exclusive. That is a very important point about the mutually exclusive. Right? So it must be the pairwise mutually exclusive. Here it is written EI intersection EJ is equal to phi for IJ, right? For all IJ, such that I is not equal to J. Clear about the mutually exclusive? Means the occurrence of one event will preclude the occurrence of the another event. That is the mutually exclusive. Then the random experiment are also characterized by the property of the statistical regularity that I have already discussed. That is for large independent trials, related frequency of event approaches the stable limit. Stable limit means a constant limit. Means when we repeat the experiment for the large number of times, n tends to infinity, for large number of independent trial, the relative frequency of number of the favorable event divided by the number of number of the experiment repeated, na upon na, right? Then that tends to the stable limit. Stable limit means if it is the constant, then we say it follow the statistical regularity. And this ratio is known as the pa, right? So pa is what? Limit n tends to infinity, na upon n, a constant value. So that is the definition of the probability, right? Depending over the frequency. But this definition will not work for the application. So we have to define the probability in the different way. And some basic property of the probability, always it lie between 0 and 1. The probability of the certain event is always 0. The probability of impossible event is always probability of certain event is always 1. Probability for the impossible event is always 0. And if if we have the union of the events and events are mutually exclusive, then we can say the probability of occurrence of the event is equal to summation of probability of the all events. Probability of all events. So let us see all these property one by one. So before uh, seeing the means detail of the probability theory, first we define the most important definition of the probability. That is the axiomatic definition. Axiomatic definition, right? So what is the axiomatic definition? So in the axiomatic definition, we will cover the relative frequency definition also. So before the axiomatic definition, we have to understand the following terms. First, sigma field. So what is the meaning of the sigma field? A class or family F of the subset of the omega containing, means here we define a family, a class F of the any subset, because subset is what? Event. So of any event of the sample space omega that contain the sure event, that contain the impossible event, closed with respect to countable intersection or countable union, right? Closed with respect to countable intersection, countable union, and countable and the complementation. Closed with respect to complementation means if you take the intersection, that resultant should also belongs to family F. If you take the union, so resultant should also belong to the family F, and complementation also belongs to family F. So let us assume if we have any event E of the sample space omega. So if you want to find the family, so it must contain the sure event, it must contain the impossible event, that set should be there, that event should be there, and it should be closed with respect to complement. It should close with respect to complement. So this is the smallest sigma field for a event A of the sample space omega. Means if you take any two events, right? Any three events, all the four events, if you take the intersection, union, right, complementation, all are the member of this family. Means omega intersection phi, omega union phi, omega complement, phi complement, all are the member of the family. If you take the omega and A, their union, their intersection, their complementation, right? All are in A. Means any combination you take, all all the three countable union, countable intersection, and countable or the complementation, all are in this family. So we can say this is the smallest sigma field for the event A of the sigma field or of the sample space omega. So here it is written, let A be non-empty subset of the omega, then the sigma field corresponding to this will be the omega phi A and A dash. If we have the two events, let A and B the two unequal non-empty proper subset of omega. Then the sigma field will be the it must contain certain event, it must contain impossible event, there must be the those events A and B, their complement must be there, their union, right? So all kind of the union, there must be the all kind of the union, and all kind of the intersection must be there. So that is the countable means countable union, countable intersection. Means now if you take any two element from the family, right? There or any number of elements, not only the two, any number of elements, their countable union, their countable intersection, their complementation also belongs to that family. That is the sigma field. So here the Borel field, the smallest sigma field on the real line R containing all the intervals of R, open, close, semi-open, finite, infinite, is called the Borel field. Right? It is the nothing, it is the sigma field over the real line. It contains all kind of the intervals, whether the open interval, closed interval, semi-open, finite, or infinite, are known as the Borel field. So now we can define the probability in the with the axiomatic approach. So axiomatic definition of the probability. So that definition is means most acceptable definition of the probability. So you know that what is the axiomatic? What is the axiom? Axiom is a statement which is always true, need not require the proof. It is the means we have the three important terms: theorem, lemma, and axiom. So axiom is the statement which do not require the proof. Always we assume that it is the true. Theorem is the statement which require the proof, and lemma is the statement which also require the proof for the proof of the theorem. Right? Lemma always we use for the proof of the particular theorem. Right? But axiom is the statement which never require the proof. Always we assume that it is the true statement. So now axiomatic definition of the probability for a given sample space omega, for a given sample space omega and sigma field f, and the sigma field f, a probability p. Now we define the probability p. A probability p on order pair sigma field and order pair of the means sample space and the sigma field is a function. Here we define a p as a function from the sigma field to a real number 0, 1, right? To a real number between 0 and 1, satisfying the following axioms. Satisfying the following axioms. So we have the following axioms. A first axiom: if E is if E belongs to F, then probability of E lie between 0 and 1. So it is the axiom of, not exactly between the 0 1, just you say the probability of E greater than 0. So that is the axiom of non-negativity. Axiom of non-negativity. Axiom of non-negativity. Then probability of certain event is equal to 1. That is the axiom of certainty. Axiom of certainty. Then if EI are pairwise mutually exclusive and belongs to sigma field F, then probability of probability of occurrence of the at least one event, probability of occurrence of the at least one event, that is the countable union. Countable union P of E1 union E2 union En is equal to P of E1 plus P of E2 plus P of En. So that is the, and that you can extend for the uncountable union also, right? Both are the same kind of the things. Only the main thing is here the all the event must be the pairwise mutually exclusive. Means probability of I from 1 to infinity of EI is equal to summation of probability of the EI I from 1 to infinity. So if any function satisfying these three or four axioms, then we say that function is the probability. And probability always be defined from the F to a real line between 0 and 1, or real interval between 0 and 1. The order triplet, sample space, sigma field, and the probability function is called the probability space, and members of F are called the events, and member of the F are known as the events. Member of F are known as the events. Now, theorems on the probability. So these three or four statement are the axioms. All the other are the theorems now. So here theorems of probability means we are not going in the proof of this, because just we have to use all these things. So we are revising all these things. So here probability of complement is equal to 1 minus probability of the event when E belongs to sigma field. P of impossible event is 0. Probability of impossible event is 0. If the event E1 implies the E2, if event E1 implies E2, I have already told you this is the E1 implies E2, right? Means if this is the E2, so this is your E1. So here E1 is proper subset of the E2, then always the probability of E1 less than equal to the probability of E2, and probability of E2 minus E1, probability of E2 minus E1 means this portion E2 minus E1 is equal to probability of E2 minus probability of E1. If E1 and E2 are two arbitrary events, P of E1 union P of E2, right? So it is the general law of addition. General law of addition. General law of addition. So probability of E1 union E2, it is equal to the P of E1 plus P of E2 minus P of E1 intersection E2. There I think I have not written the third axiom. What is the third axiom? So here the third axiom is nothing. It is the axiom of additivity. Axiom of additivity. So here we have the three axioms: axiom of non-negativity, axiom of certainty, and axiom of additivity. Over these axioms, we can define the probability. Now, if the E1 is superset of the E2, E2 is superset of the E3, and so on, right? En minus 1 is superset of the En, then the infinite intersections is equal to phi. Then limit n tends to infinity, p of En is equal to 0. From the probability, we have another important term, conditional probability. Conditional probability, as the name prompt, here we have the probability, but under some condition. So let omega fp are the probability space, means sample space, sigma field, probability are the probability space. Then the conditional probability of the event E1, given that event E has already occurred. I have told you in the conditional probability that we have the condition that event E has already occurred. Now you are interested. E has already occurred. Now you are interested for the probability that what is the probability of occurrence of the event E1. What is the probability of occurrence of event E1 when event E has already occurred? So that is the condition. That is the condition. So the conditional probability of the event E1, given that event E has already occurred, we represent it as a probability of E1 given E. Never please write as a E1 oblique, right, E. It is a straight line. Given we denote by the straight line, and it is nothing. It is equal to the probability of E1 intersection, probability of E intersection E1 divided by the probability of E. So here we have the probability of E greater than 0. What it represent? E has already occurred. Then only the probability E greater than 0 already occur. So from here we have the partition of the sample space. So what is the meaning of the partition of the sample space? Let omega fp be the probability space. The family A1, A2, An of events is said to be partition of the omega if the following conditions are satisfied. What are the conditions? Each event must be, right? Event must be the pairwise mutually exclusive, and their countable union must cover the, right, must cover the complete sample space, and each event has the non-negative, has the positive probability. Means what is the meaning of the let us have the, this is the sample space. Let is the first event, second event, third event, fourth event, right? Let us say A1, A2, A3, A4, A5. So here you can say that AI intersection AJ is equal to phi. All are mutually exclusive, and A1 union, A2 union, A3 union, A4 union, A5 will give you the complete sample space omega, and the probability of any event, probability of AI greater than 0. So it means here the A1, A2, A5 are the partition of sample space omega. So such kind of the things are known as the exhaustive exhaustive events. Exhaustive events. So in many book you will find it as a mutually exclusive and exhaustive. Means we are talking about the partition, right? There is no other events. There is no other events. For example, even and odd are mutually exclusive and exhaustive events in rolling a die, right? Other than the even and odd, there is no other event. These only there are only the two kind of the events. So that is the partition. So for the today, here we stop. In the next class, we continue with this part. Any doubt from this part? Have a nice day. Now you may leave. If you have any doubt, you can ask. Otherwise, you may leave. What you are asking, one student has asked sigma field about the sigma field. You can open your mic.
So I was asking
What
the
you want to
sigma
ask?
field, the fields that we were taught in field theory.
Sigma field. Please repeat the question.
Are
Sigma
the
field.
fields that we were taught in the field theory?
Which theory?
Field theory, so in which there are rings in algebra.
Actually, from there only we have had the idea.
Okay, so the operations we use are intersection and union.
Huh?
Okay, sir.
So what
Thank
is
you,
the
sir.
doubt in that? What is the doubt in that?
No, so I was asking about the fields only.
Okay, okay. Means that same thing. Whatever you have studied in the algebra.
Okay,
Actually,
thank
here
you.
we are means dealing the probability theory through the sigma field or Borel field.
Okay, sir. Thank you, sir.